What happens when AI learns to train itself at exascale, prune its own reasoning paths before wasting compute, and even evolve compact, interpretable algorithms from scratch? In this episode, we dive into 3 striking papers that push AI in very different directions. Billion-parameter interatomic models trained at unprecedented scale, a smarter way to cut down parallel reasoning costs, and an LLM-driven system that discovers zero-shot inference code for events and time series. Together, they reveal how efficiency, scale, and interpretability are reshaping what AI can do. Let's explore the first paper, Breaking the Training Barrier of Billion-Parameter Universal Machine Learning Interatomic Potentials. Breaking the Training Barrier of Billion-Parameter Universal Machine Learning Interatomic Potentials reports the first exascale training of billion-parameter universal MLIPs with force-matching second-order derivatives on 473 million atomic configurations spanning molecules, crystals, catalysis, MOFs, and direct air capture chemistry. The model, MATRIS-MO, extends the invariant MATRIS architecture into a sparse mixture of experts system with task-aware embeddings, charge, spin embeddings, top K element routing, and multi-head self-attention, enabling multitask learning while preserving rotational and translational invariance. Its 10M parameter precursor already set a benchmark on MapBench discovery with F1 0.847 and RMSD 0.0717, plus 13 times faster training than prior UMLIPs. The main novelty is Janus, a hybrid training stack built for double backward UMLIP optimization at scale. Janus combines FS3D, which unifies fully sharded data parallelism, graph parallelism, and expert parallelism, with just-in-time, sparse expert planning, deferred gradient synchronization, atom type aware, FP16, communication, compression, and kernel fusion for neighbor gather, edge aggregation, attention, and MOE dispatch combine. On CNIS and line-shine exascale systems, the code reaches 1, 2, over 1. 0 EFLOPS at 24%, 35.5% of peak in single precision, over 90% parallel efficiency, and normalized throughput of 653 times to 3,202 times relative to UMA. The 11.5B model is trained over 1,000 steps with 2,974 EFLOPS on 30 million samples, and the system reports 2.7 times, 5 times step time reductions after optimization. Performance scales to 1.05 EFLOPS on CNIS and 1.2 EFLOPS on line-shine in weak scaling, with sustained performance of 762.3 pflops and 1,033.3 pflops, respectively. Accuracy remains strong across MatCalc, Wiggle 150, GMTKN 55, X23, OC20, NEB, and MOFSIM bench, showing that billion-parameter UMLIPs can now be trained efficiently without sacrificing cross-domain generalization. Let's explore the second paper, Cut Your Losses, Learning to Prune Paths Early for Efficient Parallel Reasoning. Cut your losses. Learning to prune paths early for efficient parallel reasoning argues that parallel reasoning wastes most of its compute on prefixes that have already become irrecoverable. The paper first formalizes path pruning as prefix-level rejection in a standard self-consistency pipeline and introduces a 2-axis taxonomy, signal source, external versus internal, and learnability, non-learnable versus learnable. This yields 4 types, and the authors identify the previously unexplored quadrant learnable internal pruning as the key gap. They instantiate that quadrant with STOP, a lightweight super token for pruning module. STOP freezes the backbone LRM and adds a single stop token, a LoRa critique adapter, and a scalar classification head. At Inference, it uses a launch check resume protocol, generate short prefixes, score them from the cached KV states, then keep only top K paths for completion. Training supervision is built from Monte Carlo rollouts with K equals 32 continuations per prefix, producing soft success probability labels rather than hard binary labels. Across DeepSeek, R1, Distill, Quen models at 1, 5B, 7B, and 8B, and GPT, OSS, 20B, STOP, consistently beats external heuristics such as SlimSC and external PRMs such as Labor. On AIM 2.4 with DS, Quen 2, 5 to 1. 5B, it raises AVG at 8 from 30.1% to 37.92% while cutting tokens by 73.88%. On GPT, OSS 20B, AIM-25 rises from 70.99% to 75.42% with 71.62% fewer tokens. Under fixed budgets on AIM-25, GPT, OSS 20B improves from 84% to nearly 90%. Stop also reduces verification overhead to 0.2s per check versus 1.13s for type 2 and 0.38s for type I. The paper further derives an empirical scaling law for optimal retention ratio, gamma as a function of compute budget, prefix length, and task length, and shows generalization to ZebraLogic and AIMO 3 tool use settings. Let's explore the third paper, EVIL Evolving Interpretable Algorithms for Zero-Shot Inference on Event Sequences and Time Series with LLMs. EVIL introduces LLM-guided evolutionary program synthesis for dynamical systems inference, searching over pure Python NumPy heuristics instead of fitting neural networks. Using OpenEvolve with a GPT-5, GPT-5 mini ensemble over 100 iterations, it discovers one amortized dataset agnostic inference function per task that runs zero-shot at test time and is fully interpretable. The paper evaluates 3 problems: next event prediction for marked temporal point processes, rate matrix estimation for Markov jump processes, and time series imputation. On point processes, the evolved heuristic combines smooth mark transition tables, mark-conditioned inter-event gap statistics, recency-weighted local gaps, and Laplace smooth priors. It matches or beats strong baselines such as ANHP, NHP, IFTPP, dual TPP, CDIF, HawkSem, and even the pre-trained FIMPP on several benchmarks. On taxi, EVIL reaches 0.91 accuracy with lower SMAPE than deep baselines, and on unseen Mimic 2 with 75 marks, it attains 87.8% accuracy, outperforming all compared neural models despite being evolved with at most 22 marks. The runtime gap is stark. EVIL evaluates in 5 seconds on 1 CPU core versus 964 seconds for FIMPP on an A100 GPU, roughly a 200 times inference speedup. For MJPs, EVIL estimates initial state distributions from smooth counts and constructs Q from exposure times, exit counts, and recency-weighted destination statistics. On the discrete flashing ratchet, it recovers V, R, and B near ground truth, and its entropy production curves track the true dynamics more closely than FIM-MJP. For imputation, EVIL uses motif retrieval for long gaps plus time-aware linear interpolation for short gaps. It is competitive on pointwise missing benchmarks and outperforms FIM on several held-out datasets, though it is weaker on windowed motion capture gaps where learned priors help more. Overall, the novelty is not a new predictor class, but the demonstration that LLM-driven evolution can discover compact, reusable inference code with competitive accuracy, minimal data, and orders of magnitude lower compute. That's a wrap on today's AI paper highlights. Thanks for watching.